Good evening, everyone. Again, before we start off with the presentation, let me introduce our esteemed speaker for today's event. We have with us Prabir Kumar Sen sir. Prabir Kumar Sen sir has done his master's in mechanical engineering from NIT Durgapur and has over 50 years of experience in the HVAC and art industry. Currently, he is working as a freelance HVAC domain expert to leading international consulting firms. He is also working as a freelance HVAC consulting engineer. Mr. Sen has worked as Associate Vice President with Sterling and Wilson Private Limited, as Regional Business Development Manager with Voltas Limited, as Chief Engineer with Development Consultant Private Limited, Kolkata. Mr. Sen has also worked with Cooligan Corporation USA and Egypt, and with Samsung Heavy Industries with South Korea. So we are very much happy and we are very much obliged to have Prabir sir with us today. And the floor is all yours, sir. And I'm sure that all the participants who has joined today will gain much knowledge from this session which you have planned. The floor is all yours, sir.
Thank you. Thank you, Marco. So let me just see whether the slideshow works with the participants or not. Just let me know. I'll share my screen.
Yes, sir.
Okay.
The screen is visible, sir.
Good evening, everybody. The topic that we'll be going through today is heat load calculation. This is the fundamental of any HVAC project. This is the starting point of any HVAC project. So nowadays, heat load calculations are done mostly on softwares, but I would suggest that you must know, all the beginners must know the basics of heat load calculation and then work with the software so that they can work better with the software. So my basic objective of this lecture is to give an orientation on the basics of heat load calculation. Behind every air-conditioned room, comfortable air-conditioned room, there is a continuous heat and moisture flow. The heat is in both the forms, sensible heat and latent heat. You must be already knowing what is sensible heat and what is latent heat. Sensible heat is the heat that you can sense. It's raw heat. You can touch a hot object and feel that yes, it's hot. So that itself, that is a sensible heat. So there is a continuous flow of moisture and heat from outside also, and there is continuous generation of sensible and latent heat within the air-conditioned space. This is seen in the photograph or the picture which has been given in this slide. So how the heat is coming from sun through the glass, then sun through the exposed walls, then through roofs, then through floors, then partition walls, etc. And people working inside, they are generating heat. Light switched on inside, they are also generating heat, and all kind of equipment which are there inside, they are also generating heat. So there is continuous heat coming from outside, and there is continuous heat being generated from inside. So this total heat which is being generated inside and which is being, which is coming from outside. Can you see me? Can you see the slide?
Yes, sir. Yes, sir. The slides are visible.
Okay. Sir. Okay. So the total heat which is being generated inside and the total heat which is coming from outside, all taken together is called the heat load or the cooling load for an air conditioning plant. And basic objective is of today's lecture is to estimate that cooling load. So heat comes in all the three ways. by conduction, by convection, and by radiation. And we have to remove this heat is coming in continuously. So we have to remove the heat also continuously. And that we do by supplying cold air in the room. We supply cold air in the room that picks up all the heat from within the room, and then it gets heated up and we take that air out. So this is how we supply the air inside the room. Say from top of the ceiling we supply the air, it comes within the room, it picks up all the heat from the room, and then we take it out. So it takes away the heat. It takes away only the sensible part of the heat. So sensible heat being taken out is equal to mass into specific heat of air, mass of air, that means the mass of the air which is being supplied here. This is the specific heat of the air which is being supplied here, into T1 minus T2, where T2 is the temperature of the supplied air, which is less, and it's getting heated up, and T1 is the final room temperature, which is equal to the temperature of the air which is leaving the room. So if we know how much is the sensible heat within the room, and we know the specific heat of air, and we know both T1 and T2, we can find out how much air we can supply. So if we can find out what is the sensible heat, we can find out how much air we should supply how much cold air we should supply in the room. And we take this air out, and it's not a once-through system. We don't take the air out and throw it in the atmosphere. We take it back, recool it, and send it back to room. The return air is recooled by passing over a cooling coil. How we recool it? We recool it by passing over a cooling coil. So this is what a cooling coil is. So we take the return air back and pass it over the cooling coil. We recool it and supply it. And the sensible heat is taken out by the cooling coil. Yes. So latent heat part of the heat load is not taken away by the supplied air. The latent heat part of the cooling coil is taken out by condensation in the cooling oil. Latent heat means it's water vapor, moisture in the air. So when the air passes through a cooling coil, the moisture in the cooling coil condenses and it comes out. It comes out. And we drain the moisture, condensed moisture out. So temperature, size, and design of the cooling coil shall be such that it can condense out the desired amount of moisture from the room air. Just a second. What is that? I got a chat. Please share.
Please, sir, proceed.
So, yeah. Sorry for the interruption. What I was telling, that cooling coil is used to recool the air which we are taking out from the room. We are recooling it and supplying it back to the room. Latent is not taken out from the room by the cold air. It has to be taken out directly in the cooling coil by way of condensation, as you see in the picture. So latent heat is taken out by condensing the moisture within the air, and we drain out the condensate. And cooling coil size, design, and construction shall be such that it can not only cool the return air, it can also take out the desired amount of moisture by condensation. So design of cooling coil has to take care of both. Now, next. Or just press the next.
One sec, sir. Yeah.
Whether I say next, you just press. Yes. Now let us go to some basics of air conditioning. So air conditioning is a system. It is used to reverse the natural flow of heat. What is the natural flow of heat? Natural flow of heat is that heat flows from hotter area to colder area. But in air conditioning system, we take out the heat. We take out the heat from colder area to hotter area. God wants that heat should flow from hotter area to colder area. But we have to act against the wish of God. We have to take out the heat from colder area to hotter area. From an air conditioned room to outside. Outside is hotter. So we have to do it by applying a system which is called air conditioning system. Next. Orko, next.
One sec, sir. I have to reshare the screen. So there is an issue with the PPT, I guess. One sec.
Is it?
It's coming. Yeah.
Yes. And evaporation of refrigerant causes cooling. Next. How it is done? It's done like that. We have a compressor, then we compress the refrigerant gas because we have to evaporate the refrigerant gas. So how we do it? First we take the refrigerant in a compressor, we compress it. When we compress it, it becomes hot. So it becomes quite hot. So we take out that heat by passing the hot refrigerant gas over through a coil and cool that coil. We can cool that coil, which is also called condenser. So we can cool that coil either by air or by water. When we cool that condenser coil by air, we call it a air-cooled condenser. And when we cool it by water, we call it a water-cooled condenser. And the refrigerant which comes out from the condenser coil is now little cold and it's high pressure, high temperature, liquid kind of refrigerant. Then we pass it through an expansion valve, which expands the refrigerant when it passes through it. So sudden expansion of refrigerant causes cooling. It becomes gas and it gets cold. So cold refrigerant is then again passed through another cooling coil, which is called evaporator, where the refrigerant is in the form of cold gas and little bit of cold liquid. And when we pass the return air from the room over that coil, then the liquid refrigerant, whatever liquid traces of liquid refrigerant which was there in the mixture which is coming inside the coil, that also gets evaporated. That's why it is called evaporator. And then the refrigerant gas comes out of the coil as pure refrigerant gas at low pressure, low temperature vapor, and then it goes to the compressor and the cycle is on. We go on doing like that. And we supply the cold air from the evaporator coil, which comes out, we supply it to the room. So this is called a vapor compression cycle. Next. Yes. This is a direct expansion system. This is a direct expansion system of air conditioning system. So here you can see a compressor and compressor motor driving the compressor. Refrigerant goes to the condenser. It is cooled by air-cooled condenser. Then it comes to an expansion valve. From 3 to 4 line, there is an expansion valve. And expansion valve expands the refrigerant suddenly, liquid refrigerant suddenly. So that expanded refrigerant is fed directly into the cooling coil, and we pass air over the cooling coil, which cools the return air from the room, and we supply that air back to the room. So as the refrigerant is directly expanded into the cooling coil, we call it a direct expansion system. So there are other systems also, we'll come to that. Next slide. Here, the everything is same, it's chilled water system. Here everything air-cooled chilled water system. Here you have compressor, you have air-cooled condenser, you have refrigerant gas, you have expansion valve, which expands the refrigerant gas coming out from the condenser, but it's not directly fed into the cooling coil. It goes to another heat exchanger, shell and tube kind of a heat exchanger, which is called evaporator here. Here the refrigerant is expanded and we cool water in that evaporator. We cool water in that evaporator. And we take that cold water to the room where we need to cool, and there we pass the cold water through a cooling coil and then pass air over that cooling coil to cool, pass the return air from the room over that cooling coil to recool it and supply it back to the room. And the water coming out from the cooling coil gets little hot, little warmer, because it has cooled the return air. In turn, it has become hot, little warm. So we take that warmer chilled water back to the evaporator, recool it, and supply it back to the cooling coil again. This is done by a pump, which is called chilled water circuit, chilled water pump. So here, the advantage is that if these premises that you need to cool has got various rooms spread out over the premises, then taking refrigerant to a longer distance to various rooms for cooling is not very effective, because the refrigerant may get heated up, and compressor may need to be very high pressure compressor. So to avoid that, what we do, we first cool some water by expansion of refrigerant gas, and we take that cooled water to various areas for using in the cooling coil. So this is called a chilled water system. Chilled water system can be again of two types. One is air-cooled chilled water system, where the condenser is cooled by air. There is another system which is water-cooled chilled water system, where the condenser is cooled by water. So we'll see it in the next slide. So please go to the next slide. Yes. This is, everything is same again with the previous one. Only the condenser part, we cool the condenser by water. Condenser is, again, it's a shell and tube heat exchanger. Shell and tube heat exchanger, where the refrigerant is in the shell and water is flown through the tube inside that shell and tube heat exchanger, and water flows through it. Water cools the refrigerant, and it becomes part of little warm refrigerant liquid when it comes out from the condenser. But in the process, water gets heated up. So we don't throw out that hot water. We take that hot water back to a cooling tower. So a cooling tower is an equipment where the water is sprayed from the top. Water is sprayed from the top, and there is a fan which sucks air. So air and water, they maintain a cross flow. Water is coming out from top and air moves from bottom to the top or across the water flow. So it cools that spray of water coming from the top of the cooling tower, and water gets cooled. Condenser water, hot condenser water gets cooled, and it is collected at the bottom of the cooling tower, where we have a cooling tower basin. It is collected in the cooling tower basin. We take it by a pump and flow it through the condenser. So it's a water-cooled chilled water system. So this is the basic of air conditioning that I thought that I must recapitulate with you before we go to the next workout on heat load calculation. So next slide. This is the complete air conditioning system. So you go to you just see the bottom left corner where we have a compressor. We have a compressor, and from compressor, the refrigerant goes to a condenser. Condenser is cooled by condenser water pump, which supplies water from the cooling tower, and the water is taken back from the condenser to the cooling tower. Then refrigerator gets cooled. It comes down from the condenser to the evaporator, and in evaporator again we supply water, which is called chilled water. We supply it by a chilled water pump, which gets cooled, and we take that water to the air handling unit where we have cooling coil. So we supply the water in the cooling coil where we cool the return air taken back from the room. You can see on the top there is a room. So we are taking the return air back from the room and we flow it over the cooling coil, recool it and supply it back to the room. And the chilled water gets little warm. We take it back by the chilled water pump, pass it through the evaporator again, recool it and resend it. And in the winter, in some places where we need heating also, we have a heating coil which is being fed by hot water. For that, there is a boiler and a hot water pump. You can see it on the right side of the air handling unit. And air is supplied in the room by ducting. You can see there is extensive ducting on the room. So it supplies the air through supply air grills or diffusers. You can see them also in the drawing. And on the left-hand side of the room, you can see some return air ducting, which takes out the air from the room and take it back to the air handling unit for recooling. So this is the overall view of an air conditioning system. Next. Now, what is happening? We supply air in the room, cold air in the room, air gets hot, we recool it in a cooling coil. So for room air, room heat is coming to the cooling coil. And cooling coil, what we have chilled water, if it's a chilled water system. So chilled water gets warmer. We continuously flow chilled water gets warmer. So we take the chilled water back into the evaporator and recool it by refrigerant. So room heat comes from the room by air to the cooling coil, from where it is taken again by the chilled water and it goes to the evaporator, which heats up the cold expanded refrigerant gas, and that refrigerant gas becomes hot. We take it back to the compressor, we compress it, it takes further heat from the work done on the refrigerant by the compressor. Then we take the refrigerant to a condenser where we cool it by water. It is a water-cooled system. So heat from the room comes to the cooling coil, then from there it goes to the evaporator, from there it goes to the condenser, and then the heat is taken out by water and the heat is finally dissipated in the atmosphere by the cooling tower, hot air from the cooling tower. So this is how the heat moves from the room to the atmosphere through cooling tower via cooling coil of air handling unit, then through evaporator coil, that is the chilled water coil, then to the refrigerant, then to the condenser coil, then to the condenser cooling water, then to the cooling tower, and then finally to the atmosphere. This is how the heat transfer takes place. Next. Next. So, what we say that we supply cold air in the room. You see, cold air is being supplied in the room by diffuser. It picks up the latent heat. It picks up the latent heat from the room. It removes the latent heat from the room. And then we take the air back. With red arrows, you see, we are taking the air back in a cooling, to pass it over a cooling coil. The cooling coil is housed inside an air handling unit. We call it air handler or air handling unit. So in the air handling unit, we take the air return or the return air from the room and mix some outdoor air with it. Why outdoor air? Because the room will have occupants. They need some oxygen for breathing. Now, if we don't give outside air continuously, after some time, there will be shortage of oxygen and the people will start feeling uncomfortable. So we need some outdoor air continuously. Not only that, you know, we take some outdoor air and you see return air we are taking some, say, Q quantity, Q1 quantity. We apply some Q2 quantity of outdoor air with that. We add. So my supply air will now be Q1 plus Q2. Q1 plus Q2. So we are supplying Q1 plus Q2 quantity of air in the room through the diffuser, but taking back only Q1 quantity. So the Q2 quantity we are not taking back to the air handling unit. We are allowing it to leak out from the room through wherever there are openings, like say from the bottom of the door, from around the window, if there are openings. If somebody opens the door and goes out, air will only come out from the room. Room will remain little over pressure. Room will remain in little over pressure. So whenever there is an opportunity, air will only leak out from the room. Air inside the pressure inside the room will be little, slightly above the ambient pressure. Room will be over pressure. So whenever there is an opportunity, air will come out from the room. No outside air can enter into the room when you open the door, or if there is a leakage source, if there is an opening. Air will only come out. So we do it intentionally. Why do we do it? So if we allow the air to come inside the room from outside in an uncontrolled manner, then it will take out the outside dust also inside the room. That means the cleanliness of the air-conditioned room will be disturbed. Instead of that, what we do, we make the room pressure little above the outside atmospheric pressure, so that air never comes in, air always goes out. There is no infiltration of the air. There is an exfiltration of the air all the time. So the room remains cleaner. So this is how the air circuit is. So we supply the cold air in the room, take it back, pass it over a cooling coil inside an air handler or air handling unit, which has also got cooling coil and fan, and then we mix outdoor air with that and supply it, recool the whole thing and supply it back to the room. Next. Handling unit, take the returned air back to air handling unit, add some outdoor air, recool it there and send it back to room. Next. This is a continuous process. We have to do it continuously. Next. And we have to run the air handling unit, we have to run the chiller unit for supplying the chilled water. So it's a continuous process, and our expenditure is also continuous. It's not that you switch on the AC and keep it for some time and then switch it off and don't spend money on your electricity bill. No, it's not going to happen like that. It's a continuous process because heat is coming inside the room continuously. We'll have to take it out continuously, and we have to also spend continuously. Next. Yes, this is an air handling unit. This is an air handling unit. First of all, you see the most discussed item of the air handling unit, component of the air handling unit, the cooling coil. Cooling coil can have refrigerant, cold refrigerant gas within it if it's a direct expansion system. And if it's a chilled water system, it will have chilled water in it. Then we have returned air coming in the air handling unit. We mix outdoor air. You see from the left-hand side, outdoor air is entering. So we mix it in this part. It's called the mixing box. Then we filter it because outdoor air will bring in some dust, and inside also there may be dust generation. We pass it over the cooling coil. And if you need winter heating, you also have heating coil. Then we have fan, and then the fan supplies the air in the room through ducting. The whole thing is housed in a box, and that complete box is called an air handling unit or air handler. Next. Now, mixture of return air and outdoor air, we pass over the cooling coil. How the cooling coil looks like, it has got copper tubes, and over the tube we have fins stacked, at very close interval, say 10 to 14 fins per inch length around that. So there are aluminum fins over it. And the right hand side, you see the actual photograph of a cooling coil. where you have the coil, copper tube, and over it there are fins. So fins are little, corrugated shape like this, and the air flows over it. So when the air flows over it, we make all the arrangement. We try our best so that air is fully cooled. What do you mean by fully cooled? Air temperature, air which is coming out from the coil, will have same temperature of the coil. But unfortunately, we can't do that. Though we try, we have coil, we could have left it at the coil only. But to increase the cooling surface area, we have added fins, and so many fins. We cannot increase it more, because if we increase the number of fins, then it will provide resistance, enormous resistance to the airflow. So my air handling unit fan has to be very high pressure. Very high pressure means very high power and very high power consuming. So there is a limit. So it's around 10 to 13, 14 fins per inch length. And we have made the fins little corrugated so that when air passes over it, it bounces in the flow path. It becomes turbulent. There is no laminar flow. If it becomes turbulent, then the heat transfer is better. But still some air manages to bypass the cold surface of the cooling coil. That means the cooling coil tube and the cooling coil fin. Some air manages to bypass the cold surface and comes out totally unaffected. Totally unaffected. And the percentage of total air which comes out from the cooling coil totally unaffected is called a bypass factor of the cooling coil. In general, 12% of the about 12% of the total air being passed over the cooling coil bypasses the cooling coil. So we call bypass factor 0.12. Next. The fresh air part, we consider this bypass air in two parts. One is the fresh air part, because the air which bypasses the cooling coil has, is a mixture of outdoor fresh air and return air. So, for our easier calculation effort, we split it into two parts. One is the fresh outside air. So the fresh outside air, part of the fresh outside air, which is hotter than the return air. Return air, if we set the room temperature at 24 degrees centigrade, then the return air temperature will be 24 degrees centigrade. But outside air will be, if the outside temperature, like in Calcutta a few days ago, it was 42, 43 degrees centigrade. So 42, 43 degrees centigrade outside air. So part of that also bypasses. So that part of the outside air comes to the room directly through the ducting. So it adds heat load in the room directly. It adds heat load in the room. It adds both sensible heat by the high temperature of 42 or 43 degrees centigrade a few days back in Calcutta, and also the moisture part. Calcutta is very famous for its humid weather. So that means that the outside air has got high humidity, high moisture level. So that moisture brings in the latent heat along with it when you take the outside fresh air. You want fresh air for oxygen, but along with that, you get bonus heat and moisture, which is a problem for you, bonus problem. So you have to tackle that problem. It comes within the room again through the cooling coil by bypassing the cooling coil. If the bypass factor is 12%, then 88% of the air, we can, hot air, even the outside hot air, we will cool it in the cooling coil, but 12% manages to bypass the cooling coil and comes straight within the room and offers and adds both sensible and latent heat to the room. So we have to take care of that. So you know what is bypass factor, and return air also a bit of it bypasses, 12% similar. And that bypasses means, air which is coming out from the coil, if its temperature is say 12 degrees centigrade, if its temperature is 12 degrees centigrade, air which comes out from the cooling coil, it should have been, cooling coil temperature is normally around say 10 degrees centigrade. So 10 degrees centigrade temperature coil, it cannot produce 10 degrees centigrade cold air coming out from it because of these reasons, because of some air bypassing, and there are other reasons also I'll be discussing in the next slide, but let us for the time being consider because of some air being bypassed. So this bypass air contains two parts. One is the outside air, which we'll be considering in the heat load being directly added in the air conditioned room, and one is the return air. Return air temperature is 24. So some amount of 12% of 24 degrees centigrade air comes straight unaffected through the cooling coil. So cooling coil outlet temperature will be little more because of that, and it will never be equal to the cooling coil body temperature. So that's how the cooling coil temperature, body temperature, if it is, there is a term for that cooling coil body temperature. We call it apparatus dew point. We'll come to it later on. So cooling coil body temperature or apparatus dew point, whatever we call it, whatever name we give it, if it is 10 degrees centigrade, the air coming out from the cooling coil will be little more than that because of these reasons, and it will be around 12 degrees centigrade. So let us go to the next slide. Last slide, we say that, some air is generated within the room, some air is, some heat is generated within the room, and some heat comes from outside to the room. And we have also discussed supply air, and we have also discussed return air. Now we have to understand that heat is coming, but whole of the heat is not coming within the room straight away. Some heat is coming straight away within the room, and some heat is coming in the return air portion of the room. So this is a room we have shown. You see, the bottom part is the room, indoor room, room indoor. And then we have false ceiling. We have a false ceiling. Above the false ceiling, we have a dark colored air handling unit, inside which there is a cooling coil. And there is a fan which supplies air, and we take it through a ducting and supply it by a supply air diffuser. You can see the blue color diffuser with blue color supply air, cold supply air. And then we take it in the return air, by return air diffuser, red return air, supply air, let us say 12 degrees centigrade, it picks up all the room heat and becomes 24 degrees centigrade. So if the mixing of air inside the room is proper, so anywhere in the room, you will get 24 degrees centigrade. But if you take the supply air blast directly, then it is not 24 degrees centigrade, then it is 12 degrees centigrade. You will feel colder. So that's why when I suggest anybody to install an air conditioner in his bedroom, I say, no, don't put the air conditioner over your bed or over your head in the bed, because you will get a direct blast of 12 degrees centigrade air. So you will feel colder. You will feel colder. So put it away from your bed so that it picks up all the heat of the room and becomes 24 degrees centigrade. Becomes 24 degrees centigrade. So that 24 degrees centigrade air, which is shown by the red air, goes up above the false ceiling, which is the return air space. And it is taken out in the room. So heat comes in two ways. One part, it has got two parts. Now, next. Okay. Yes. So heat comes in two parts. One directly in the room, which we call room total heat. One in the return air space, which is the return air total heat. And room total heat again has got two parts. One is the sensible part, another is the latent part. And the return air also, total return air heat also has got two parts. One is the sensible, one is the latent part. Now let us see which heat comes where. I will tell you why I am splitting it. Why I am splitting it? Because whatever heat comes in the room, particularly the room sensible heat, that has got a special importance. What special importance? That heat we will take out by supplying cold air in the room. The cold air we supply in the room to take out only the sensible part of the room total heat part. So we'll have to separately calculate room sensible heat to determine how much air we should supply, how much cold air we should supply in the room. And that will determine my air handling unit fan capacity. And that will determine my supply air ducting sizes. And that will determine my supply air drill or diffuser sizes and numbers. And that will also play a major role in sizing the chiller. And the heat which is going to the return air part has got nothing to do with how much cold air we supply in the room. But that air also has to be cooled. That heat also has to be cooled. That heat also has to be cooled by the cooling coil. So cooling coil has to be sized for both total room total heat, that is sensible and latent, because sensible heat, we have to recool the return air, which is picking up heat from the room. So room sensible heat finally has to be cooled in the cooling coil. So that will form one part of the work of cooling coil, one part of the cooling requirement of the cooling coil. Then the latent heat from the room, by way of moisture, it goes in the cooling coil, and it has to be also condensed out by the cooling coil. So that will also form one part of the cooling requirement of the cooling coil. And then the return air, both sensible and latent heat, which we are adding in the return air part, that also has to be cooled in the cooling coil. So cooling coil has to do everything. So cooling coil sizing has to be done on the basis of all the heat. And cooling coil sizing, how much cooling has to be done, dictates the size of my chiller. Chiller has to supply that much of cooling. Otherwise, cooling coil itself can't cool. It's only a support service. It provides a support service. But basically, cooling is done by chiller. So my chiller sizing depends on my room total heat plus return air total heat. And my air handling unit fan sizing is dependent on only the sensible part of the room total heat, which we call effective room sensible heat. So effective room sensible heat, there is a twist at the end. It will be coming in the next line, next paragraph, when Marco shows it. What is effective room sensible heat? Effective room sensible heat, not just the sensible heat being added in the room. This also includes sensible heat from the outdoor air, which bypasses the coil. And heat gain in the supply air ducting. You see, the supply air ducting coming from the AHU to the supply air grill, taking the blue air in the room. So that ducting also has got heat gain, and sometimes the supply air duct gain, and in addition to that, there is a fan motor. Air handling unit has got a fan. So fan motor is there. So depending upon the location of the fan motor, we'll discuss in the next slide. Depending upon the location of the fan motor, air handling unit fan motor, we have to add heat of that fan motor either in the return air side or in the room sensible. Because fan motor is not generating any moisture. It's giving only raw heat. So it gives only sensible heat. So that sensible heat from the fan motor, where it will come, whether it will come to the supply air part, I mean the room sensible heat part, or it will go to the return air sensible part, that we'll see. But that has also to be taken. And all these taken together is called effective room sensible heat. And this effective room sensible heat determines the size of the air handling unit fan. Next. Room total heat plus room return air total heat will determine the cooling coil size and tonnage of the plant. That's what we told already. So when you determine the size of your air conditioning plant, that is tonnage of the air conditioning plant, you have to consider all the heat. Next. Now, location of the fan motor. I have shown two types of air handling unit. You see, by red lines, I have shown return air coming inside the air handling unit, return air plus outdoor air coming inside the air handling unit, and the other one is the supply air. Now, for the left one, left air handling unit, first we have the cooling coil, then fan, then outlet. There will be filters, etc., which is not shown. And the second one, you see, we have fan and then cooling coil. Return air, then fan, then cooling coil, then it goes out. So, the left one, what is happening? The air is first cooled. So, cooling coil is done, cooling is done. And the air handling unit fan is after that. So after the cooling is done, my fan motor gives it. So that will not come in the return air. That will straight away go to the room air, that heat of the motor. So that will be added to the effective room sensible heat. It's a called draw-through configuration of air handling unit. Draw-through means it draws air through the cooling coil. It draws air through the cooling coil. So if your air handling unit is of draw-through construction, then add the fan motor heat in the room sensible heat. The other air handling unit, you see, the return air comes, it also picks up the air handling unit fan motor heat, then it passes over the cooling coil and cold air goes inside the room. So, return air itself picks up the fan motor heat before it passes over the cooling coil. So here, the fan motor heat will come in the return air part of the air conditioning system. So this is called a blow-through configuration of air handling. Here, the fan is blowing air through the cooling coil. Fan is blowing air through the cooling coil. So you must know what kind of cooling coil you are using. So better to use, blow-through configuration of the cooling coil, because why unnecessarily, supplying the fan motor, taking the fan motor heat in the room air means it has to be taken out again by supplying some extra amount of cold air. That means it will increase my air handling unit fan capacity. So if there is no specific reason, better to use a blow-through configuration of air handling unit. Next. So it depends upon where the heat will go, it depends upon the AHU construction. Next. Now, slowly will be, so long we have been discussing the peripherals of heat load calculation. But these are very fundamentals. You must know it. Then only you can take decisions. So far we have been arming you with various ammunitions. So once you get fully armed, you can tackle the heat load calculation in much better way. Now space cooling load. Next. We said there are external loads, loads which are coming out from the external sources. There are internal generation of heat. So what are the external heat? Heat gained through exterior walls or roofs, direct solar radiation through windows. That means the direct sun which enters the room through the window. Sun cannot enter through exterior walls. It only makes the exterior wall hot. And that hot wall radiates through inside. But the glass window, if it is there, a portion of the heat directly comes in the room. Through the sun directly coming in the room through the window. Additionally, the window also gets hot and radiates it inside the room. So windows have double effect, glass windows, and the walls or roof has got single effect. Next. Heat gain through internal partitions or doors. Internal partition and doors means the partition walls and doors which separate the air-conditioned room from an adjacent non-AC room. If the adjacent room is also non-AC, is also AC, and both are running together, then the partition walls, on either side of the wall, the temperature is same. So there will not be any heat transfer. But if the partition wall segregates your air-conditioned room with a non-AC room, then heat will come through that. Next. Infiltration of outdoor air, including bypassed air. So, if some air leaks inside the room, which normally will not, as we discussed, that our basic intention is to make the room positive pressure. Then outside air will never enter the room, so infiltration will be zero. Next. Infiltration is zero when ventilation air is more than the infiltration air. That means room is under pressure. But there are some exceptions where room is intentionally kept under negative pressure. Suppose you are trying to keep a COVID patient inside a room, inside an air-conditioned room. So, if you make that room over pressure, so wherever there is leakage, air from that room will leak out and bring out the COVID infection from the room to outside areas, which you don't want. So you make those kind of people with infectious disease inside a room where the pressure has to be negative, less than the outside ambient pressure. So that wherever there is a leakage, whenever somebody is entering inside the room, opening the door, outside air will always go in and inside air will never come out. And there is no opportunity of infection being spread out from the patient, infectious patient, which is who is staying inside that room. But otherwise, in normal condition, unless you want the outside air not to come in, if there is some radiation inside the room, you are having some radioactive experiment inside the room, or there is an infectious patient inside the room, then the ventilation air is more than the infiltration air. You have to decide how much air we should supply in the room. That consists of two parts. One is, how much is the oxygen requirement for the person, breathing requirement, plus what is the normal leakage area. So even my air continuously leaks out through that area, still I can maintain some positive pressure inside the room. So we must supply that much air also along with the breathing requirement air. So ventilation air shall always be more than the filtration air for positive pressure rooms. And in those cases, infiltration is 0. Next. Then internal loads. Internal loads are people, electric light, equipment and appliances. Then. Next. All these along with the bypass here, inside here, internal load means all these along with the bypass air and supply air system heat gain, fan, air duct from the effective forms the effective room total heat we discussed. A part of which is effective room sensible heat and the other part is effective room latent heat. Next. Effective room sensible heat is used to determine the supply air fan capacity, air handling unit fan capacity. And made statistical analysis and come out with suggested outdoor design condition. Next. See, ISHRAE 2021 data for Kolkata. There are many things. I have just kept it two things. One is the cooling requirement, another is the evaporation requirement. For the cooling requirement, which will be basically used for air conditioning, we have 0.4%, 1%, 2%. These are occurrence level. So we have data for 0.4%, we have dry bulb temperature and mean coincident wet bulb temperature. For all the 0.4%, 1% and 2%. Now 0.4%, if we select 0.4% dry bulb temperature, for Kolkata, it is 37.9. So if we consider design outdoor dry bulb temperature for Kolkata as 37.9 degrees centigrade, then all over the year, rather all over the, not year, all over the reasonable life cycle of AC plant, only on 0.4% of the time, the outdoor temperature, dry bulb temperature will exceed 37.9. So we call it 0.4% occurrence level. Similarly, if we consider 1% occurrence level, you see the dry bulb temperature is 36.9, 1 degree centigrade less. That means if we consider 36.9 degrees centigrade dry bulb temperature as design outdoor temperature, dry bulb temperature for a Kolkata location air conditioning system, then 1% of the time for a reasonable life cycle period of AC plant, the outdoor temperature will be more than 36.9. And 2% occurrence level, it is 35.9. For comfort air conditioning, we normally consider 36.9. But for very specific cases where the temperature variation, if the outdoor temperature goes up, what will happen? My room temperature will go up. Because my AC plant is undersized for that temperature. So it will not be able to cool properly. And for very specific case, where even for a very short time, we can't tolerate that higher temperature, slightly higher temperature, then we should go for 0.4%. Otherwise, for general application, it is 1%. For offices, hotels, hospitals, residences, schools, everywhere normally we consider 1% occurrence level. Dry bulb temperature is 36.9 and corresponding to that we have to consider a wet bulb temperature which we call mean coincident wet bulb temperature, 27.5 degrees centigrade. ISHRAE has collected data from various meteorological stations and they have made a statistical analysis of dry bulb temperature and found out what will be the temperature which is included within 99% days, 99% of the time. That is 1% occurrence level. So that they found 36.9. And then they found that if we fix the 36.9 degree centigrade dry bulb temperature, when it occurred actually, then what were the wet bulb temperature during that time? So they have made mean of that wet bulb temperature. That is 27.5. So 27.5 is the mean coincident wet bulb temperature. That means it is expected that the wet bulb temperature at 36.9 degrees centigrade dry bulb temperature will be around 27.5 degrees centigrade. So my design condition for Calcutta, outdoor design condition for Calcutta will be 36.9 degrees centigrade dry bulb temperature and 27.5 degrees centigrade wet bulb temperature. It will raise a question. The DCR, it has gone to 42, 43. Yes, let us see. 42 and 43 it has gone, maybe half an hour a day. For this year it is extreme, maybe 15 days a year. So half an hour into 15, so maybe 7.5 hours over the year, this year, because of El Nino effect, which is occurring this year. It may not happen next year. So let us see. If it happens consecutively for 2-3 years, then ISHRAE will definitely review their design condition. Maybe in ISHRAE data for 2025, we'll have different set of data. Like this is the New Delhi design condition. It is also given. Next. Some more data for Mumbai, Chennai, and Bangalore. Similarly, ISHRAE and NVC has got similar data, design outdoor condition. I don't think ISHRAE or NVC has got updated data for 2021. They might have, they normally, use ISHRAE data and use it. ISHRAE and NVC. ISHRAE, of course, definitely works out on some more Indian stations, Indian locations beyond what ISHRAE has done. And NBC data is 2016 data. NBC data is 2016 data. I think by now those data has become obsolete. So better we must consider ISHRAE 2021 data and wait for ISHRAE to come out with updated weather data. Next. Next slide, yes. So for normal air conditioning work, that is for cooling and dehumidification design condition, we consider design dry bulb temperature and mean coincident wet bulb temperature. We have discussed it. Next. For evaporative cooling, we consider the wet bulb temperature and mean coincident wet bulb temperature. You saw the other set of data, evaporative. So those data we have to consider for cooling by air washer or desert cooler kind of thing. So those data we have to consider. And even for sizing the cooling tower, we have to consider that evaporative cooling data given by ISHRAE. Next. There are dehumidification work. For that, ISHRAE has also given another set of data where they have given dew point and mean coincident dry bulb and humidity ratio. So those we have to consider. For dehumidification work, we are not going to discuss that in detail in this lecture. Next. This is some NBC data, which is older, 2060 data. Similar data. Next. Now, we have fixed up the outdoor design temperature. Now, inside design temperature. ISHRAE 55 has given inside design temperature. They have suggested some. They have done extensive research with various people, how they feel comfortable, with what kind of clothing they are feeling comfortable. So they have given some data. Next. This is a graph. You see the darker one, this is the clothing factor 0.5. That means, lighter clothing lighter clothing, you can go for little higher temperature and humidity, and the light shade one, that is clothing factor 1, that is for the reasonably heavily clothed. You can go for a little lower temperature, set the little lower inside temperature. Next. ISHRAE, if you have seen that graph, the temperature they have suggested between 24 to 26 degrees centigrade. Now, India has become very active, Government of India and Bureau of Energy Efficiency, they have become very active on power saving. You set your air conditioner at lower temperature, means, you will be continuously consuming more power. Okay, you will be paying the bill for it, no doubt, but it's a total damage to the society and the environment, because power, power comes along with a baggage. Baggage is damage on environment. Power generation, unless it is eco-friendly power generation, renewable power, which we hardly use for air conditioning. So it comes only by fossil fuel fired power, which pollutes our environment. So India government is very conscious about it, and they have put a locking on the air conditioning areas inside temperature. They have suggested that all commercial buildings and residential buildings shall have inside design temperature of 24 degrees centigrade. And nowadays, if you go and buy an air conditioner from the market, split AC or window AC from the market for your home, there the initial temperature setting of your AC is locked at 24 degrees centigrade. So, and they suggest that you keep it at 24 degrees centigrade. Don't change it to 22 degrees centigrade. Next. B suggests that we should keep the room temperature to 24 to 25 degrees centigrade. I would rather opt 25 degrees centigrade because it saves energy. It saves electric bill. That's a direct benefit to the user, and it saves the environment. That's a benefit to the mankind. So better you set it at 25 degrees centigrade. Rather, don't put on suit, three-piece suit in your office. Try to use short sleeve shirt and no tie in your office, and set the office temperature at 25 degrees centigrade. Setting temperature at 25 degrees centigrade or 24 degrees centigrade will save about 25% of the energy. Imagine. Next. Flu-like viruses that also survive shorter in higher temperature and humidity. In fact, in COVID situation, ISHRAE was suggesting that you set your AC temperature even higher than 25 degrees centigrade. You set it at 27, 28 and run the fan. Run the fan. So that, if by chance any virus comes inside the room, that will also survive lesser or lesser period in that higher temperature. Next. That's what I have said. That during, yeah. And sometimes MCC room, unnecessarily we set the temperature 22 degrees centigrade. Electrical rooms, control rooms, it's not needed. Talk to the manufacturer. They will say 28 degrees centigrade is okay. Have a word with the supplier of the panel or the MCC or server, what temperature they want, and set it. In some of the recent projects, I have seen large office buildings being done by very reputed builders in Bangalore and Madras and Bombay. They were air conditioning the leak machine room. I told, call the leak manufacturer. OTs and all those guys, they were called in. I asked them, did you need air conditioning for your lift machine room? They said no. It can work up to 45, 50 degrees centigrade. I said, then why are you air conditioning the lift machine room? Not needed, just ventilating. So talk to the equipment supplier before you go for whether air conditioning or ventilation, and if air conditioning, then at what temperature. Don't go blanket. No, it should be also 24. Oh, no, it's control room, it should be 22. Don't go blindfolded like this. Next. Many occupied electrical rooms may not need air conditioning. That's what I said. That lift machine room doesn't need air conditioning. Nowadays, even with all very sophisticated control lifts with very sophisticated controllers, they don't need air conditioning. Next. Now, inside temperature we discussed. Now inside relative humidity. This is a fantastic figure which shows a green corridor between 40 to 60% RH. That means all your infections are minimum at 40 to 60% RH. There are some infections which increases when you decrease the relative humidity, and there are some infections which increases when you increase the relative humidity. But there is a green corridor, 40 to 60%. For looking at human health, we should keep the relative humidity between 40 to 60%. For the general office areas, general residential purpose areas, we should keep 40 to 60% relative humidity. Next. Now, low RH is very bad. High RH is equally bad in electrical equipment room. Low RH generates statical electricity. You all have experience that if the RH is low, the statical electricity is generated. I tell you my current experience. I am currently in USA. I am speaking to you, I am talking to you from USA now. And I am staying in a place where it is currently summer, and in the noon hours, the outdoor ambient humidity goes to 22-23%. And here, it's not that big summer like in India. Currently, in the noon hours, the outdoor temperature is 23, 22, 24 degrees centigrade. So sometimes I go outside and sit in the backyard on a chair, which is synthetic chair. It's made with artificial canes, synthetic canes. So I sit there, and whenever I have polythene short, synthetic shorts, and I rub my body on the chair during movement, I get a little bit of shock, electric shock. Because of the low humidity, static electricity is generated. It's not that big, but I can definitely feel it. And similarly, you also might have some experience of low RH situation. So low RH situation, static electricity is extremely bad for electrical things. Because nowadays we have printed circuit boards and very compact ICs, integrated circuit, where conductors are placed, two conductors are placed very closely. So if RH is low, there is a chance that there will be sparking. There will be static electricity generation and sparking in between two conductors, closely spaced conductors. And because of that sparking, it may cause short circuit. And when the RH is high, say 80% RH inside the electrical room, that may at times create condensation of water on the cold surfaces. And that condensed water may again cause short circuit between two closely spaced conductors or electrical elements of an IC or a PCB. So, electrical rooms also should have controlled relative humidity. Next. If RH is low, it produces electric discharge, static electricity discharge. Next. RH is high, water condensation. Next. So, intermediate area is between 40 and 60%. So we should try to keep RH of electrical load between 40 and 60%. You see the gap there. Next. Generally, RH is kept between 40 and 60% with alarm provision when the RH goes below 30% or goes above 70%. Next. Next. Solar radiation through windows and skylight. They also give sensible load. Next. Conduction through ceiling, interior partition, walls, and floor with non-AC areas. Again, sensible load only. Next. People give both sensible and latent because when we breathe out, we give heat, hot air, and also it contains moisture. So we give out moisture and sensible heat and latent. Lights, again, only sensible. Next. Equipment and appliances. Next. Yes. It can give sensible and latent, mostly sensible if it is computer and control panels, etc. It is sensible, but if we use any equipment which also deals with water, then it may give out some latent heat also. Next. Infiltration air. If there is infiltration, outside air coming in. Outside air coming in means it will bring in both raw heat, sensible heat, and moisture, that is latent. Next. Ventilation air, that means outside fresh air. For intentional, infiltration is unintentional, uncontrolled air coming in. And ventilation means I have decided the quantity and I have controlled it and I have given it with a specific purpose. That is the ventilation air. So ventilation air also brings in sensible and latent heat. Next. System heat gains by fan motor, friction in the supply air ducting, those are all sensible heat. Next. Now, building heat gain. I will take half an hour more. I think you will bear with us because we started little late because of some technology glitch. Okay?
No issue, sir. Please continue.
Yeah, because we are in such an interesting, or I don't know whether it is boring, but we are in a very critical stage of our discussion. So let us not stop. It's already 8 o'clock at your place, 10:30 in the morning at my place. So we'll continue for half an hour more, right?
Yes, sir. Please.
Heat transmission through wall and roof or similar construction items can be expressed as heat transmission equal to UA delta T, where HT is the heat transmission. It can be in BTU per hour or watts. Next, U is the overall heat transfer coefficient. We also call it U factor, which has got a unit of BTU per hour per feet square per degree Fahrenheit or watt per meter square degree Kelvin. BTU per hour per feet square per degree Fahrenheit means this is so much BTU per hour for every square feet area of the building material for each degree temperature rise. And if it is the SI unit, watt, it includes your, calories per hour. And then calories per hour, kilocalories per hour, in fact. Kilocalories per hour per meter square area per degree Kelvin temperature rise. Next. A is the area of the surface. Next. Delta T is the temperature difference between outside and inside. If outside is 43 and inside is 24, then 21 degree centigrade is the delta T. The overall heat transfer coefficient, U factor, describes how well a building element resists heat or reduces rate of heat transfer through unit area of the structure per unit difference of temperature, unit degree difference of temperature This is called U factor. So from the equation HT equal to UA delta T, you can see the lower the U factor, the lesser is the heat transfer. So we would prefer lower U factor. That means we would prefer to use a building material which has got lower U factor so that outside heat coming inside will be less. Next. You see, high U value, high heat flow. Low U value, lower heat flow. How we have made it lower U value? We have wall and then we have insulated it. Insulated it. Insulation of wall is not very common in India, in our country. But where I'm staying now in US, because of severe cold here, not only for air conditioning, but for severe cold winter, all the building walls are insulated. All the building walls are insulated. Okay, next. U value is the inverse of R value. Thermal resistance, inverse of thermal resistance value is the U value. Next. So, if we have a wall and an insulation together, how we find the total U value of that? We take the resistance value of all the elements of that wall, that is brick, then insulation, we add them together, sigma R, and then make inverse of it. Get the U value of the wall, insulated wall. We'll do a workout in subsequent slide. U is the heat transfer coefficient. Okay, next. U is inverse of sigma R for a wall or a roof which has got composite components like brick or RCC, then insulation, then over insulation, some coating, etc. So we have to take the R value of each component of the construction material and then add them together, then take inverse of the summation to get the U value of the composite material. Next. R is the resistance I told. Next. Typical U value factor for wall. Let us see. You consider a wall, Indian wall. What we have? Outside air film. Outside air film. That also offers a boundary layer, which acts as an insulation, which acts as a resistance to heat flow. So thermal resistance of that is 0.044. We have taken this 0.044 from ISHRAE, or ISHRAE also has got this value in their handbooks. So resistance of outside air. Next. Then after that outside air film, we have outside plaster, half-inch plaster, 13mm plaster. For that, R value is 0.018. Next. Next we have common brick. Common brick we have. For that, we have 250mm common brick. 250mm common brick wall, for which we have 0.279 R value. Next. Then we have inside plaster, half-inch, again 0.018. Then we have inside steel layer, for which inside air, which is 0.12. You see, outside air, R value is less than inside air. Why it is so? Outside air is turbulent because continuously there is wind flow. So turbulent boundary layer has got lesser resistance to heat. That means heat flows to the heat transfer is more in turbulent boundary layer. That's why we have made the turbulent boundary layer for cooling coil fins. And inside air is reasonably still, calm and quiet, no air draft within the room. It's calm and quiet, no storm, no outside air movement inside the room. So it provides a more or less laminar boundary layer. So it has got more resistance to it. So these are the typical elements of our simple looking wall, building wall. If you come to USA or any other cold country, you have to add another element here, insulation, thermal insulation, which is not there in Indian buildings. Next. Next, yes, total R. So adding all these together is 0.47 times. And inverse of that is 2.086. So U value for outside wall is coming as 2.086. This is watt per meter square degree Kelvin. Next. These are certain, ISHRAE, copy from the ISHRAE pages. How I have taken the R values. Like you see, wall is vertical. So if it is vertical wall, then non-reflective, then outside air is 0.12. Sorry, our steel air is 0.12. Steel air is 0.12. So steel air, this is steel air. So for inside wall air film, I have taken resistance as 0.12. You have seen it in the previous slide. Similarly, for outside air, they have considered two wind velocities. One is little windy condition, 6.7 meter per second. Another is little not windy condition, 3.4 meter per second. So I have considered 3.4 meter per second outside wind velocity. There, the R value for the outside steel air is 0.04. So I have taken that from, I have also given the reference, page number 26.1, ISHRAE fundamentals. This is little old, but I think this has not changed over the years, 2009 edition. Next. Next slide. This is again for the plastering material. You can see 0.72 is the resistance, and the brick 0.81 to 0.96. I have taken some average like that. So these are the references I have given. Next. Now, how actually heat transfer occurs? Our calculation, what we said, heat transfer equal to UA delta T. But it's not that simple. It's not that simple. We have to modify that equation a little bit. So how the heat transfer occurs? The heat falls on the wall of the roof like that. Some part is reflected. Then the wall of the roof gets heated up. When it gets heated up, from inside surface to outside surface, the heat, outside surface of the wall, heat flows by conduction, and the whole thing gets heated up, then it starts radiating. When it starts radiating, some it goes outside, some it comes inside, and when the sun goes out in the evening, then also the wall remains hot, and the radiation of heat still goes on. Still goes on. So then delta T is not that big. Sun has gone down, outside temperature has fallen down, but the walls are hot. Walls are still remaining hot and will still keep radiating heat inside. So heat load will come in. Again, in the morning hours, the walls have become cool. Outside has become cold, but the outside wall is taking a little time to get heated up. So in the morning hours, though delta T is low, the heat dissipation in the room will not be that big. Heat coming inside the room will not be that big, because the walls are still not that hot. It's still remaining little cold. And throughout the year, throughout the seasonal change, throughout the day, this will happen. So it's slightly complicated. So what will be the heat load? Next. So this is what I have discussed, that heat is being, falling solar radiation on the outside wall, partly reflected, then it is getting heated up, then hot wall radiates heat inside and outside, and when outside surface of the wall gets heated up, then air coming in contact with the inside air coming in contact with the inside surface of the outside wall, the air gets heated up and it's hot air starts moving and a convection current comes in. That convection current of air that circulates the heat inside. So all these things are happening. Next. So we will be replacing delta T. Instead of temperature difference, we'll be using a term called total equivalent temperature difference to take care of all these phenomena. And all these phenomena will vary depending upon the building material construction. So if you are using, heavy wall, which will take longer time to get heated up and longer time to get cooled down. So that will have different kind of phenomena. It will also depend upon the location's daily range of temperature. Some places temperature vary quite a lot. Like here where I am now staying, the morning temperature is 10 degrees centigrade and the noon temperature is 24, 25 degrees centigrade. So 14, 15 degrees centigrade temperature range, temperature variation. But in Calcutta nowadays maybe 5 degrees, 6 degrees centigrade temperature range. So if temperature range is more, then your building material gets opportunity to cool down more and then pick up heat again. But if the temperature range is not that big, your building material doesn't get cooled much. So your heat transfer pattern will be different. So instead of that, let us take the total equivalent temperature difference instead of actual delta T. Next. This was my earlier equation. So taking care of all these things, we will use TETD instead of delta T. TETD for various locations are available. Various locations are available in ISHRAE or carrier handbook. It is available. It depends upon the location of the place. Location means its latitude of the place. It depends upon the density of the building material. It depends on the color of the building material, dark color, light color, all given. Daily range of the location. So daily range you can find from the weather data in ISHRAE weather data, whatever I have given. Then in those pages there are other columns which gives daily range also. So you see the daily range and go by the daily range and find out TETD. I will show you at the end of my lecture. I will discuss some Excel sheet where TETD, how we calculate, are shown. Next. So this is how the heat transfer through building wall and roof has to be done. UATETD. Next, heat gain through glass and windows. Glass and windows I have said. Next. The part of the light falling on the outside surface, it gets reflected, but part comes directly inside, which doesn't come directly inside for walls or roofs. Other phenomena are same. The glass will get heated up, radiate heat inside, outside, all these things are same. So, transmission, direct transmission is a very big part. So we have to take it. Next. This direct transmission we can reduce. If we don't use a curtain, almost 80% of the heat comes directly in the room. Solar radiation, 80% comes directly in the room. If we provide a curtain from inside, we can cut it down to 50%. If we provide a curtain from outside, we can cut it down to 15%. But we don't provide curtain from outside because of operational reasons. Next. But yes, in other countries, they provide this kind of shed from outside. And in our countries, we provide shed over window. The shed construction is this kind. Chhaja. Chhaja we provide like this. Sunshade also we call it. You see, it has provided shed over the window. The right one. Right photograph at the bottom. Yes. We do like this. It cuts down a bit of heat. Direct solar radiation doesn't come in. Now, direct solar heat gain through glass, which is direct solar radiation coming in, is area into solar heat gain factor into shading factor. If you are using curtain, then each curtain has got a shading factor. So area into solar heat gain factor into curtain. Solar heat gain factor is a measure of how much heat the glass allows. It depends upon the type of glass, latitude and location, direction of window, north, south, east, west, and year and time of the day. In our air conditioning calculation for Calcutta, we consider normal glass, latitude is 22 degree latitude. So we consider 22 degree latitude for Calcutta. And direction of window, for each window we calculate. North, south, east, west, every direction we take window, and for that we have different solar heat gain factor. And month of the year, we consider the hottest month of the year. In Calcutta, we consider June to be the hottest month of the year. Next. It depends on the type of curtain we are giving. It is 0.56 for light color Venetian blind or uproll curtain from inside. Next. Additionally, there is transmission. I said, so far the solar heat gain through glass area into solar heat gain factor into shading factor. This is the direct solar radiation which is coming inside. Additionally, like other building material, walls and roofs, the glass window will also become hot and heat will come inside because of that. So that also has to be added. So how is that? Let us see. Next. That transmission is like similar to glass and wall. Area into delta T into U factor. Because glass is very thin and normally we don't take TETD. Because of that, we take only delta T and U factor. Very thin glass, and major portion of the radiation comes through the direct radiation. So only a relatively less portion comes, so we don't go for TETD there. We take only delta T. Next. Delta T is different than the difference between outdoor and indoor. Next. U factor for 3.8 millimeter thick glass, single pane glass is 2.48. Nowadays, for large commercial building, we are using very special glasses, which are reflective glasses. Reflective glasses also, people are objecting nowadays because it reflects most of the heat, but it creates glare. So your outside environment becomes glary, and heat reflected from your building may fall on the adjacent building. So people are objecting to reflective glasses, but there are other glasses which passes only very minimum amount of heat. So very special glasses are there. So if we use them, we must consult, we must consult glass manufacturer's catalog and take the U value from there. But normal clear 3.8 millimeter single pane glass is 2.48. We hardly use double pane glass in our country yet, though we have started. New kind of windows have come. They are advertising everywhere, even in Calcutta, to use double pane glass, but we are still not catching up. But in this country, in USA, all windows are double pane. Next slide. Double pane glass will have lesser heat transfer coefficient. You see, these are a few graphs for the double pane glass. So U factors are given. U factors are given. You see, the top curve is, 12.7. Top curve is for double pane glass of clean glass with air inside. Next one is argon inside. Next one is argon inside. And next one is krypton inside. Double pane glass with krypton gas, inert gas inside. And the last three curves are, next three curves are for air, argon, and krypton, but the glass used is not clear glass, it is low glass with low emissivity. That's what I am telling you. So normally, what I see in this country and optimum also, they say that half-inch gap between the two panes of the glass in the window, 12.7 millimeter, and it's normally air. So 12.5 millimeter with air will give little less than 3 U factor. But if you use argon or krypton, you get lesser. But if you use low emissivity glass, yes, there are low emissivity glass. That's are also very common in this country. Low emissivity glass, that means we'll have to go to the next three curves. There, if you use air gap in between, low emissivity glass, you can see from inside. You can see everything outside from inside. But from outside, you cannot see the inside of the building. Much. You can't see much. So there, with with air gap inside, the U factor will be less than even 2. Next. Low emissivity coating combined with krypton gas, that means the lowest curve, will give you much lesser U value. Much lesser U value. It's even less than 1.3. Very good. Very good. Next. Now, heat gain from other sources. So we have covered heat gain through building envelope, which includes walls, roofs, and glass windows. Then partition will be same as walls. Instead of TETD, for partition you consider only delta T, because direct solar radiation is not falling on the partition wall. It's only temperature difference between the AC room on one side of the partition wall and non-AC room on the other side of the partition wall. Floors are also same. If the floor below is non-AC, then temperature difference between the AC room on one side of the floor and the temperature of the non-AC room on the other side of the floor. You take that delta T. Now, there are heat gain from other sources. Heat gain from people. You see, if you are sleeping, you are releasing less heat. If you are working on a table, you are releasing little more heat. If you are moving and if you are doing exercise in a gym, you are releasing even more heat. Next. So people engaged in normal office work releases sensible heat of 75 watts and latent heat of 55 watts. We can consider it for our calculation. Each people, 75 watts sensible heat and 55 watts latent heat. If there are 10 people, we should multiply it by 10. Unless in an office, next, your boss makes you work like this, we consider 75 and 55. But if your boss makes you work like this in an office, of course, heat released by you will be more. Next. So heat generated by people, it is given moderate active work, standing, doing light work in some workstation, shop floors, then light bench work, heavy work, exercise in gymnasiums, etc. It's given here. You can consider these values. Next. Heat gain from lighting. We must understand lighting a bit before we go to heat gain from lighting. I'm going a little detail because you see, these are the basics. Once you make this clear, then you can work with any kind of software with much more confidence and you can exercise your decisions, judgments. You don't have to work like a donkey or with some software. Then you get garbage in and garbage out. Next. So when we use lighting, we use light for convenience of our seeing things. So for that, lux is the importance. Lux level of the place. 1 lux is equal to the illumination level of a surface 1 meter away from a single candle like this. That is 1 lux. A moonlit night has got 1 lux illumination. So 1 candle, 1 meter distance, 1 square meter area. Illumination is 1 lux. 1 square meter is not that important. Now, if you multiply the lux level by area, that will give you lumen. Your electric bulb, they produce lumens, not lux. If you switch on a single electric bulb in a small room, you get more light. That means more lux. Because electric lamp is producing lumen. You are using it in a smaller area. So you divide it by smaller number. You get more lux level, more illumination. If you use the same lumen for a larger area, you divide the lumen by more area to get the lux level. So you get less illumination. So illumination level is lux, but what the lamps are producing is lumen, energy. Next. So if you go at distance also, then the same lumen which can produce 20,000 lux is coming down if you go further. Next. A modern office requires about 40 lux illumination. Lux is illumination, not lumen. Lumen is what light will produce, lamp will produce. Next. An incandescent light, they produce 17 lumens per watt. Next. Fluorescent light, for same watt, they produce more light. Next. Sodium vapor light, even more watts, more lumens. LED light, even more lumens. So, just a second, go back. So, you see, watt is producing different lumens. So it looks that my incandescent light is more power guzzler. It consuming more powers and producing less light. So where the power is going? Heat, raw heat. LED light, much less heat. Next. Now you see, for an office, normally 800 lumens. If we need 800 lumens, so 800 lumens, about 800 lumens. One is 840, one is 825, another is 800. So you need a 60 watt light to produce 800 lumens. Whereas you need only 18 watt light to produce 800 lumens. You need 10 watt LED to produce same lumen. And life-wise, you see, LED lights have got more life. Annual expenditure, LED light has got minimum, though initial cost is more for LED light, but it will be offset very soon, very soon. And as because LED lights produce more lumen, so there will be much less heat in the AC space because of lighting if you use LED light. So now switch everything to LED light. Next. So incandescent light, only 15% you get light out of the total energy spent. 80%, 85% comes as heat. Halogen is this, fluorescent is this, and LED is this. Next. Office. Now, considering all these things, ISHRAE has suggested something that you can consider. If you use LED light, you can consider 60 watt per meter square for LED light. Control room, 77 watts, shop floor, 10 watts. Next, per square meter, lighting load. They have given straight away load. But you have to multiply this lighting load. If you are using incandescent light, so if you are using 60 watt light, all of 60 watt comes in the lighting, comes as heat. Even light part comes as heat. Fluorescent light, if you are using 18 watt light for the same amount of lumen, you will use 60 watts. So for incandescent light, for some amount of lighting, you consider 60 watt as the heat load. For CFL or fluorescent light, you use 18 watt light, but you have choke and starter additionally for this light. Those will be also generating heat and dissipating. So to take care of this choke and starter, you multiply the 18 watt by 1.25. So add another 4.5 watts. So 22.5 watts. So for same amount of lighting, incandescent light, you consider heat load as 60 watt, you consider 22.5 as heat load for CFL, and for LED light, for the same amount of lighting, you use just a 10 watt load. But in LED light also at the bottom of the bulb, there is a driver, an electronic circuit, which again consumes about 12% of extra energy. So multiply that by 1.12, so 11.2 watts. So for same amount of lighting, you were using 60 watt energy or 60 watt heat load for AC calculation, AC heat load calculation, 22.5 watt heat load for fluorescent light, and only 11.2 watt heat load for LED application, LED bulb application. Next. Ventilation and infiltration. So we have discussed ventilation and infiltration, but what will be the heat gain because of that? Next. Infiltration is air leakage. Next. We have discussed it. Next. Next. All these discussed. Next. Go to the next. Heat gain. Now, before we go for heat gain from the ventilation air, we must know how much ventilation air we should take. ISHRAE 62 has suggested how much ventilation air we should give for various applications. For general office space, hotel room, or auditorium, we should give 9 cmh per person. ISHRAE has given 9 cmh per person, or 2.5 liter per second per person for breathing purpose, and additionally 1.08 cmh per square meter of area, or 0.3 liter per second per square meter of area for making the room over pressure, considering a standard amount of leakage. So, CFH plus 100 square feet or say 200 square feet. So 200 into 1.08. So 200.26. Or how much? No, 108. So 216. So 10 people 900 plus for area 216. So 1116. 1116 cmh of fresh air or ventilation air you must give as per ISHRAE. So once we have decided on how much ventilation air, now we must calculate how much part will be sensible heat, how much part will be latent heat from there, and how much will come inside, directly inside the room. 12% will come directly inside the room because of the bypass factor of the cooling coil, and 88% will go in the cooling coil. So room sensible heat will be bypass factor, that is 0.12 into ventilation CMH, that is 1116 CMH into 3600 into 1.2 into 1000 into outside air drive out temperature minus room drive out temperature. So much watts. This will be coming directly inside the room as sensible heat. And some latent heat will also come inside the room. That will be dictated by the next equation. Next. Next. This is the room ventilation air. 0.12 bypass factor, ventilation CMH into 1.2 into that 234, then 4 knots. Then outside specific humidity, that means moisture content, grams per kg of dry air, outside air, and grams per kg of dry air moisture content for inside air. So much humidity, so much watts will be coming as latent heat directly inside the room. Next. Contact factor is 0.1 minus 0.12, so 0.88. So use contact factor in place of bypass factor to calculate the balance amount of heat that is going to the return air. Same formula, but use contact factor in place of bypass factor to get the balance amount of heat that will be going into the return air as sensible heat and as latent heat. Next. These are the ISHRAE tables which gives, how much liter per second per person and how much liter per second per meter square for various applications. Various applications. Next slide. Like retail stores, etc. Yes. Hotels, malls, etc. Next. So these are some copies from the ISHRAE. Next. ISHRAE also has given exhaust air. How much exhaust air shall be given from gym, sports complex because of the odor, smell, bad smell. You have to take out some air also from there. And toilets, etc. And there are some air conditioning systems like some operation rooms or some particular hospital areas where all the air is continuously there is some exhaust. So there these exhaust exhaust quantities are also given by ISHRAE, and they are also mentioned that minimum some exhaust rates are to be maintained and some exhaust distance, they have said 6 meter distance has to be maintained between the exhaust point and the fresh air intake point. Next. So with this I say thank you, not really thank you. Now we will go to the Excel sheet. We have discussed the basics of heat load calculation. Now you just see a real situation that will take maybe another 10-15 minutes and then we'll close down. I apologize very much for delay, but I think that will be very, very useful to you. So, or if you just show them the Excel sheet.
Right. Shall I show the Excel sheet, or you will be taking the screen and showing the calculations?
Yeah, you Excel sheet I will do. Okay. Yes. Yes. Can everybody see the Excel sheet? Can everybody read it?
Yes, sir.
Or
Yes,
I
sir.
need to zoom it out.
Just increase the. It's visible. Just increase the size of the Excel sheet. It will be more visible.
Font size I increase.
Yes, yes. You increase the font size, or you can on the lower right corner of the screen there is a plus sign. You can click on it. Yes.
Yes. Yes. Is it better now?
Yes, sir. Yes, it's better.
This is the heat load calculation Excel sheet. This is an orthodox method, but I think you all should use it for some time to strengthen your knowledge before you go to the software. So here, typical office building, Kolkata, a seminar hall, area, length and width, multiply, get area, a particular one. Volume, multiply it by the height. This is this. Bypass factor 0.12, contact factor 1 minus bypass factor. Then outside air for Calcutta 36.9. Mean coincident wet bulb temperature is this. So before that, I think there is another sheet. You just have a look here. Can you read it? This is the input sheet. Or I increase it further. Readable by everybody?
Yes, sir. Yes, sir. It is readable.
Okay. So this is the input sheet. We first have to work out on the input sheet. And the other sheet which I showed you before, it will pick up from the input sheet. So first of all, ISHRAE data, outside design temperature. So these two data are given in ISHRAE. I use psychrometric chart to get RH and to get moisture content or specific humidity. This is kg of moisture per kg of dry air. Then inside temperature I have considered 24, RH 50. Again from the psychrometric chart I have found out what is the moisture content and what is the wet bulb temperature inside. Then calculation of U factor. For wall, outside steel air, plaster, brick, inside plaster, inside steel air. So this was the total R and this is the total U, 1 by R. Then interior partition, again similar way. Interior partition, then roof outside turbulent air, then concrete slab, then 13 millimeter inside finish, then 25 millimeter insulation, polystyrene expanded foam. Roof shall be insulated. Inside air, steel air, then total is this, R is this, and U is this. Glass partition. Glass partition, various glass partition. This is the U factor. We have considered this. Solar heat gain through ordinary glass. Solar heat gain factor. There is for direct solar radiation. North wall is this. We have considered 20 degree north latitude for Calcutta at 3 p.m. on June. From there I have taken solar heat gain factor for this. The data I have taken from this data I have taken from carrier handbook, and I have converted into watts per meter square, because the carrier handbook gives BTU per hour per foot square. So I have converted it, and then I have considered light color Venetian blind. So this is 0.56 is the shedding factor. So if the glass is on the north window, this will be my solar heat gain factor. If it is on the south, this will be this. If it is east, this will be this. If it is west, then northeast, southeast, southwest, southeast, northwest, southeast, like this. Then equivalent temperature difference, TET, total equivalent temperature difference. So equivalent temperature difference, we have considered 504.2 kg per meter square. This is wall and 142 kg per meter square roof construction. This is density. Density we have considered. And daily range 8 degrees centigrade, inside temperature 24 degrees centigrade, outside temperature 36.9 Calcutta. So I have again considered carrier handbook for north side wall, etc. TETD are this. Then correction factor. These TETDs were given for a particular temperature inside and outside and particular daily range. So I have corrected it, correction factor, and this is my, considering the correction factor, this will be my final TETD. Lighting load I have considered this, equipment load I have considered this, occupancy for the seminar hall I have considered 19, ventilation rate I have considered 9 CMH per person and 1.08 CMH per meter square area. Now going back to the main. So this part I have done, the inside outside condition I have put, number of people I have put. Now seeing the drawing, I have seen the drawing of the seminar hall. There is a glass window on the east side. So this was the area. So multiplied by solar heat gain factor, by shedding factor. So this was my sensible load. Then south, there was no area, no glass. Only east side there was glass. So it was this wall. There was north and east side. North side wall, this is the area. East side wall, this is the area minus the glass wall. This is the area, and this is the TETD, and this is the U factor, this is the heat load, and exposed roof is there. Then the external wall, this is the partition wall, this much is the partition wall, this is the temperature difference of partition wall, this is the U factor, this is the heat load, so everything. People 90, 75 watts latent heat, 55 watts, 75 watts sensible heat per person, 55 watts latent heat. This is the total for the 90 people. This is the sensible heat. This is the total latent heat for 90 persons. LED light, I have taken it, the value from the input sheet, multiplied it by area. Input it has given watt per meter square, from there it is the area. And lighting load has come. Then equipment load I have considered 275 watt approximately. And this is the 275 watt. So all these things, I have considered some safety factor 5% on both sensible and latent heat. This safety factor is mainly because to take care of system heat gain, duct system heat gain, etc., and fan heat gain, AHU fan heat gain, etc. So this 5% is added. 5% is added, and this was the sensible room sensible, effective room sensible heat. This is the effective room latent heat. So now total heat is this. Adding all this is the total heat, and other heat gains I have considered again another 3%. So grand total is this. So divided it by the converting this watts, 35,182 watts, I have come to 10.3 tons, 10.01 tons is the plant capacity. And similarly, here the number 90 people, 9 CMH per person, so 810 CMH and 1.08 CMH per meter square. So meter square was, area was 87 meters square multiplied by 1.08 gives me additional 94. So total is my 904 CMH total air quantity, which has been considered in the calculation for latent heat and sensible heat. Then apparatus dew point, it is coming as 12.78. So we have taken 12.78 apparatus dew point. I have considered little less apparatus dew point of 12 degrees centigrade. And chilled water temperature I have checked from the chiller. They can supply 7 degree chilled water at 7 degrees centigrade. So maintaining 12 degrees centigrade coil temperature is not difficult. So I have calculated the air quantity, dehumidified air quantity from the K25. It has come from here. Where is K25? Dehumidified air quantity. It has come from essential, this is the ESH, equivalent room sensible heat, ERSH. So from ERSH I calculate the dehumidified air quantity here. So I get dehumidified air quantity and my tonnage. And here the dew point of the retired air is also calculated. It is 15.5 degrees centigrade. I have set my cooling coil apparatus dew point as 12 degrees centigrade. 12 degrees centigrade, so it is lower than the dew point of the retired air. So there will be enough condensation and room latent heat will be taken out properly. So this is the heat load calculation Excel sheet, and there is a summary sheet which gives us. Oh, I think there is some mistake here. So don't consider the summary sheet. It's a mistake. Don't consider it. So you go by the only input sheet and the heat load area sheet. Summary sheet has not been updated. So there is some cell changes. I've deleted some sheets. So it's still holding those figures. So don't consider it. So this is how the heat load calculation sheet works out. So with this, I would request you to go through my lecture once again. You can get it from ISHRAE if you like, and then go through the heat load calculation Excel sheet. I'm sure you will be able to work it out in a better way. So with this, I would say thank you once again. Thank you once again. And now if you have any question, let me see what is there in the chat box.
Do we have a few questions, sir? Actually, one question. Mr. Mritunjay Kumar has asked, please explain about the dehumidified CFM.
1 second. Where is the chat box?
It's in the question and answer section, sir, not in the chat box.
Oh, is there a question and answer?
Yes, Q&A.
Chat Q&A, right?
Right.
Yes. Please explain our dehumidified CFM. I think you asked the question much before. Dehumidified CFM is the cold air that will be supplying in the room. It's the cold air that will be supplying in the room. It is actually the air handling unit fan capacity. And once the air comes out from the room, once the air comes out from the air handling unit, it gets dehumidified because we take out the latent heat by condensation, by taking out the moisture. That means we are dehumidifying it. So we also call it dehumidified air quantity. So dehumidified air quantity is basically the AHU fan capacity, or basically the cold air quantity that we are supplying in the room. So this is what is dehumidified air quantity. My email ID, Orko can share it with everybody.
Yes, sir. So we don't have any more questions. It's already 9. So thank you, sir.
So any question, if it comes out later, I'm open to answering them through email. So don't hesitate. I may take 1 or 2 days more time, but you will definitely get the answer. This is what I promise to you. So
No issues, sir.
thank you for giving a patient hearing.
Thank you, sir. And I am writing your mail ID in the chat box for everybody. If you, I'm writing my mail ID. So if you have any questions regarding today's sessions, just email it to me. I'll just forward that to sir, and we can consolidate all the questions and get back to you. So I'm just writing my mail ID to everybody. Please send me your queries, whatever you have on this particular session. Since we are running short on time, we'll be ending the presentation here today. So thank you, sir, for this amazing presentation of heat flow.
Thank you, everybody. It has been a 3-hour session finally.
Yes, sir. It's a 3-hour long session, but it was a very interesting session, and everybody stayed on to hear what you have to say. So it was a very enriching session, and it was definitely